The cosmos carries an echo of its violent birth. This is the story of the universe's first space-time ripples, primordial gravitational waves generated in the Big Bang's initial fury. By the end, you will have a front-row seat to 30 of the most astonishing theories physicists have devised to explain this fundamental signal. We will explore why these faint tremors might reveal if our universe collided with another, or if time itself had a beginning. What does the deepest mystery of our origins make you wonder about? That echo begins with a single, powerful idea. The leading explanation for these primordial ripples is cosmic inflation, a theory so profound it reshaped our understanding of the universe's first moments. Picture the universe not even a second old, a seething, hot, and unimaginably dense speck. Then, in a fraction of an instant, it underwent a growth spurt of impossible magnitude, inflating from a subatomic point to a volume larger than our observable cosmos today. This was not an explosion into space, but a violent stretching of space-time itself, and within that stretching field of energy known as the inflaton field, the seeds of everything were sown. At the quantum level, this field was not perfectly smooth. It fizzled with tiny, random fluctuations, unpredictable jitters in energy. These were fluctuations on a scale so small they are almost meaningless to describe. But as the fabric of the universe inflated at speeds far beyond light, those microscopic quantum jitters were stretched, frozen, and imprinted onto the cosmos. They became the faint hills and valleys in the density of the early universe. Where there was a tiny extra bit of density, gravity would later pull in more matter, eventually forming galaxies and clusters. And crucially, these same quantum tremors in the fabric of space-time also generated gravitational waves, the first ripples. They are not waves in space, but waves of space, oscillations in the geometry of the universe itself, born from that primordial quantum storm. For decades, this has been the theoretical cornerstone. The smoking gun evidence would be a specific pattern, a curl, imprinted on the oldest light in the universe, the cosmic microwave background. This pattern is called B-mode polarization, a unique twisting signature that could only be made by gravitational waves passing through the primordial plasma. Experiments like BICEP and Keck at the South Pole, observing from one of the clearest, driest places on Earth, have been hunting for this fingerprint with extraordinary precision. Finding it would be a direct look at the universe when it was a trillionth of a trillionth of a trillionth of a second old. It would confirm that the grand structures we see today, from galaxy superclusters to the very ripples in space-time, began as quantum whispers amplified to a cosmic roar. Yet the hunt for that specific signal has opened a door to other, even stranger possibilities. If the primordial ripples we detect do not match inflation's precise prediction, it could point to an entirely different cosmic genesis. This is the realm of the Ekpyrotic universe and the Big Bounce, theories that replace the single, explosive birth of inflation with a cycle of collisions and rebirths. Picture our entire three-dimensional universe not as an isolated bubble, but as a vast membrane or brane floating within a higher dimensional space. Parallel to it floats another brane, another complete universe. In the Ekpyrotic scenario, our beginning was not a bang from a point, but a gentle kiss. These two branes, drawn together over eons, eventually collided. That collision transferred an immense amount of energy, setting our brain into a hot, expanding state we call the Big Bang. But the violence of that collision, the shudder of two entire realities smashing together in a higher dimension, would have sent powerful gravitational shockwaves rippling through our newborn cosmos. These would be the first space-time ripples born not from internal quantum jitters, but from an external, cataclysmic impact. The alternative cyclic model imagines a universe with no true beginning or end, only an endless cosmic heartbeat. Here, our universe expands from a hot, dense state, cools, and eventually stops. Then gravity takes over, pulling everything back in a great crunch. but instead of collapsing into a singularity of infinite density, physics at the most extreme scales, perhaps guided by quantum gravity, causes a rebound. The universe bounces, launching a new period of expansion from the ashes of the old one. Each cycle destroys and recreates the cosmos. In the moments of maximum compression during the bounce, when all matter and energy are squeezed to an unimaginable density, the fabric of space-time would be violently agitated, generating a storm of gravitational waves that carry into the new cycle. The crucial difference between these stories and inflation lies in the character of the ripples they produce. Inflation, stretching quantum fluctuations, tends to predict a very specific spectrum of waves, strongest on the largest scales. The signals from a brane collision or a cosmic bounce, however, could be markedly different. They might be louder or have a distinct pattern across different frequencies, a unique fingerprint of their violent macroscopic origin. So the search is not just for any ripple, but for the specific tone and texture of that echo. Detecting it would tell us whether our universe was born alone from a quantum seed, or from a collision with a sibling universe in a hidden dimension, or is simply the latest verse in an infinite, cyclic poem of cosmic death and rebirth. The story of creation may not be one of smooth expansion, but of sudden, violent change. Another compelling theory suggests the early universe did not cool gracefully. Instead, it underwent a series of dramatic phase transitions, cosmic shifts in the very state of reality, similar to water freezing into ice or steam condensing into droplets. In the universe's first moments, all forces were unified into one superforce. As the cosmos expanded and cooled, this symmetry broke. The fundamental forces we know today, like electromagnetism and the strong nuclear force, crystallized out one by one. Each break was not a gentle process. Think of a pond on a cold night. It does not freeze all at once. Ice forms in patches, creating bubbles of solid water within the liquid. In the early universe, bubbles of a new, more stable vacuum state would have spontaneously formed and expanded at nearly the speed of light. Where these bubbles met and collided, they released titanic amounts of energy, shaking the fabric of space-time itself. These collisions would have been catastrophic events, generating a storm of gravitational waves. Furthermore, defects could have formed in the cosmic structure, like cosmic strings, infinitely thin cracks in reality left over from the transition. As these strings stretched, crossed, and snapped, they too would have sent powerful ripples cascading through the young cosmos. This theory paints a picture of a chaotic, frothing universe, its birth marked by the violent popping of cosmic bubbles and the sharp crack of snapping strings. The gravitational wave signature from such an era would be profoundly different from the smooth, stretched hum predicted by inflation. Instead of a dominant low-frequency signal, a phase transition would produce a cacophony across a wide range of frequencies, with a distinctive peak that acts like a cosmic timestamp, telling us exactly when that transition occurred. This is where our future listening posts come in. Ground-based detectors like LIGO are tuned to hear the high-frequency chirps of black holes and neutron stars. To catch the lower-frequency rumble of these primordial phase transitions, we need to go to space. Missions like the Laser Interferometer Space Antenna, or LISA, a trio of spacecraft flying in a perfect triangle millions of kilometers apart, are designed for this very purpose. By precisely measuring the distance between them with laser beams, they could detect the gentle stretching and squeezing of space caused by these ancient waves. Finding such a signal would not just tell us about ripples, it would reveal the universe's teenage years, a turbulent period of identity crisis when the laws of physics themselves were settling into the form we recognize today. It would be evidence that our cosmos was forged not in a single, smooth event, but in a series of violent, symmetry-shattering cracks. The universe's first moments may have been seeded with traps of pure gravity. Another radical idea suggests the primordial ripples we seek are not a direct echo of inflation, but the death knell of the universe's very first inhabitants, primordial black holes. In the standard story, the density fluctuations from inflation grew slowly over billions of years into galaxies. But what if some of those initial lumps were so extreme, so incredibly dense, that they bypassed the star-forming stage entirely? These monstrous overdensities, regions where matter was packed with unimaginable tightness, could have collapsed directly under their own weight when the universe was less than a second old. They would have formed black holes not from dying stars, but from the raw clumpiness of the newborn cosmos itself. Their birth would have been a violent, chaotic process, each collapse sending powerful gravitational shockwaves through the surrounding space-time. But the story does not end there. These primordial black holes once formed would not have remained solitary. Drawn together by gravity, they would have danced in pairs, spiraling inward over cosmic time until they collided in titanic mergers. Each merger would release a burst of gravitational waves, a chirp from the dawn of time. The combined chorus of countless such mergers across the universe's history would create a persistent hum, a stochastic gravitational wave background woven from these ancient collisions. This theory connects the first ripples to two of modern astronomy's greatest puzzles. First, dark matter. Could these primordial black holes, scattered throughout the cosmos and invisible to light, constitute the mysterious dark matter that holds galaxies together? If they formed with the right range of masses, they could be hiding in plain sight, their collective gravity shaping the universe while remaining utterly dark. Second, it offers a potential explanation for some of the surprising black hole mergers detected by LIGO and Virgo. These instruments have heard pairs of black holes merging that are curiously heavy, black holes larger than we expect from the collapse of massive stars. Could these be not stellar remnants but ancient relics from the universe's first second, finally finding each other after an epic journey across the ages? Detecting the specific hum from a population of primordial black holes would be like finding a fossil record written in gravity, revealing a hidden chapter where the infant universe was dotted with gravitational singularities, their collisions ringing out to shape the cosmic background we search for today. The fabric of reality itself may contain more threads than we can see. This leads us to the profound and mind-bending possibility of extra dimensions, a cornerstone of string theory. To make the math of quantum gravity work, string theory proposes that the fundamental particles of the universe are not points, but tiny, vibrating strings. And for these strings to vibrate in all the complex ways needed to produce the forces and particles we observe, they require more space to move. Specifically, they need extra spatial dimensions beyond the three of length, width, and height that we experience. These dimensions are not vast, expansive realms. Instead, they are thought to be curled up or compactified on a scale so incredibly small, 1 billion times smaller than an atomic nucleus, that they are completely hidden from our everyday perception. Think of a garden hose. From a distance, it looks like a simple one-dimensional line. But if you could shrink down to the size of an ant and crawl onto its surface, you would discover it has a second dimension, a circular one curled around its circumference. Our universe could be like that hose, with 3 large, familiar dimensions and several more curled up so tightly we cannot perceive them. Now, apply this to the universe's fiery birth. In that first fraction of a second, all dimensions, including these hidden ones, would have been unstable and wildly fluctuating. As the universe expanded and cooled, a cosmic settling had to occur. The 3 dimensions we know unfurled into the vast cosmos, while the extra dimensions compactified, shriveling down to their minuscule, stable size. That process of stabilization would not have been gentle. It would have been a cataclysmic event, a dimensional earthquake. The energy released as these dimensions snapped into their compact shape would have been staggering, violently shaking the very geometry of space-time and generating a torrent of gravitational waves. The signature of these waves would be a direct message from the geometry of the cosmos. Their spectrum, the distribution of their power across different frequencies, would act like a cosmic barcode. By reading it, we could potentially decipher the number of extra dimensions that exist and even estimate their size at the moment they stabilized. It is a staggering thought. By listening for the faintest whispers from the beginning of everything, we might not just learn about our universe's expansion, but count the hidden folds in the fabric of reality itself, uncovering the true, multidimensional architecture of creation. But what if our three-dimensional reality is merely a shadow? This brings us to the holographic principle, a theory so revolutionary it suggests the universe we experience is a grand illusion, a projection from a two-dimensional surface. Imagine the information needed to describe everything within a volume of space. Every star, planet, and person could be entirely encoded on the boundary enclosing that space like a cosmic DVD. In this view, our rich three-dimensional world is akin to a hologram, where a three-dimensional image emerges from light interacting with a two-dimensional film. For our universe, the cosmic horizon, the farthest distance light could have traveled since the Big Bang, acts as that two-dimensional film. Every event, every particle, every ripple within the cosmos is just a translation of quantum information written on that distant spherical screen. Now apply this to the first space-time ripples. In the holographic framework, gravitational waves, including the primordial ones, are not fundamental vibrations of space-time itself. Instead, they emerge from the dynamics of quantum information on that two-dimensional boundary. The faint tremors we seek to detect would be the three-dimensional projection of quantum entanglement and information transfer happening on the universe's ultimate horizon. This idea finds a profound connection in the black hole information paradox. A black hole, according to classical physics, destroys all information about what falls into it, violating a core quantum principle. But the holographic principle resolves this by suggesting all information about what fell in remains encoded on the black hole's two-dimensional event horizon, its surface. The universe itself, in a sense, might be like the interior of a black hole, with its own horizon holding the complete information of everything within it. So, detecting primordial gravitational waves becomes an experiment in cosmic cryptography. We would not just be measuring ancient ripples, we will be decoding bits of information from the universe's outermost shell, reading the quantum script from which our reality is rendered. If this principle is true, it means gravity and space-time are not fundamental ingredients of nature, but collective phenomena that emerge from a vast underlying network of quantum information, much like the temperature of a gas emerges from the collective motion of countless molecules. Finding the first ripples could provide the first tangible evidence that we live in a holographic universe, a breathtakingly vast projection whose true workings are written in a simpler, lower-dimensional language we are only beginning to understand. Our universe may be just one bubble in an endless cosmic sea. The theory of eternal inflation takes the idea of a single inflationary period and extends it into infinity. Picture the false vacuum, that unstable high-energy state that drove our universe's initial expansion, not as a one-time event but as an eternal, self-replicating medium. In this view, inflation never truly ends everywhere. Instead, it stops in localized patches like bubbles spontaneously forming in a pot of boiling water. Each of these bubbles is an entire universe nucleating out of the inflating background with its own random set of physical laws and constants. Our observable cosmos is merely the interior of one such bubble that stopped inflating some 13.8 billion years ago. But outside our bubble wall, the chaotic inflation continues forever, constantly giving birth to new bubble universes in an endless, frothing multiverse. Now consider what happens when two of these expanding bubbles, each a separate universe with its own Big Bang, grow and eventually collide in the greater inflating medium. The collision would be a cataclysmic event on a scale beyond comprehension. When our young bubble universe was struck by a neighboring one, the impact would have transferred immense energy at the boundary. This would not have destroyed our universe, but it would have left a permanent scar on its oldest light. Theorists suggest such a collision would create a distinct imprint on the cosmic microwave background. Because the collision would come from a specific direction in space, it would not affect the CMB uniformly. Instead, it might appear as a strange, anisotropic ring, a circular pattern of slightly hotter or colder temperatures breaking the otherwise smooth, uniform glow. It would be a cosmic bruise, a telltale sign of contact with another reality. Furthermore, the violence of that collision would have shaken the fabric of our bubble universe at its inception, generating a unique burst of gravitational waves. The signature of these waves would be directional, carrying the memory of the impact's geometry. Searching for this is not just about finding ripples, it is about finding ripples with a specific story, a pattern that points to a single, dramatic event on the edge of our cosmic horizon. While we have not yet found definitive evidence of such a bubble collision in the CMB data, the mere possibility reframes our entire existence. It suggests our universe is not alone, but one island in an infinite archipelago of realities, each with potentially different physics. Detecting that faint, circular scar or its corresponding gravitational wave echo would be the first empirical hint that the multiverse is not just a philosophical idea, but a physical reality, and that our entire cosmic history began with a violent encounter with another world. Stephen Hawking offered a universe without a beginning. This is the essence of the no-boundary proposal, developed with physicist James Hartle, a quantum vision that dissolves the Big Bang singularity into something far more elegant. Instead of a violent explosion from an infinitely dense point, they imagined the origin of the cosmos as a smooth, rounded geometry, like the North Pole on Earth. If you ask what lies north of the North Pole, the question has no meaning. The North Pole is a boundary of our map, not a place in the land. In the same way, Hawking and Hartle proposed that time itself has no sharp starting edge. In their model, if you could run the cosmic film backward, time would not end at a singular, explosive moment. Instead, it would gradually become more and more like a dimension of space. In the extreme quantum fog of the universe's origin, the familiar distinction between time and space blurs away. The universe transitions smoothly from a four-dimensional, timeless geometry into the expanding, time-driven cosmos we inhabit. It is a birth without a bang, a gentle emergence from a state where the very concept of before ceases to apply. But how does this serene beginning connect to the violent space-time ripples we seek? The conditions are set in that primordial quantum blend, the transition from a timeless Euclidean geometry to a universe with a clear arrow of time is not perfectly uniform. Quantum fluctuations, those fundamental jitters inherent to reality, are present even in this no-boundary state. As the universe crystallizes its direction of time and begins its expansion, those fluctuations are imprinted onto the fabric of the newborn space-time. They become the seeds for everything, including gravitational waves. The character of those first ripples, their spectrum and amplitude, would carry a direct fingerprint of this unique, singularity-free origin. Unlike theories that begin with a violent collision or a phase transition, the no-boundary proposal suggests a more subdued, quantum statistical origin for the primordial hum. It predicts a specific pattern, one that future, ultra-sensitive probes of the cosmic microwave background or the gravitational wave background could, in principle, test. Detecting a signal that matches this prediction would be profound. It would suggest that our universe did not erupt from a singular point of infinite density, but quantum-tunneled into existence from literally nothing, a smooth geometric curve where time itself was born. It transforms the greatest mystery, the question of what came before the Big Bang, into a question without a foundation, because in this view, there was no before to speak of, only a timeless, self-contained geometry from which all of reality and time itself gracefully unfolded. The universe's first second was a crowded, seething sea of particles, Among the most abundant were neutrinos, ghostly particles that barely interact with matter. About 1 second after the Big Bang, as the cosmos cooled enough, these neutrinos finally streamed free, decoupling from the primordial plasma to form a pervasive, invisible background that permeates all of space to this day. This cosmic neutrino background is a relic almost as ancient as the light from the cosmic microwave background, a fossil from an even earlier time. Now consider the first gravitational waves, those primordial ripples in space-time, beginning their journey through this dense neutrino fog. Neutrinos, despite being nearly massless, exert a tiny gravitational pull. As a gravitational wave passes through, it slightly disturbs the neutrino sea. The neutrinos, in turn, scatter gravitationally off the wave, a subtle interaction that can subtly alter the wave's journey. This process, called gravitational scattering, could have acted like a cosmic filter. It might have dampened certain frequencies of the primordial gravitational wave background, or slightly shifted their polarization, imprinting a unique signature onto the signal we hope to detect. Think of it like sound traveling through air. The air itself doesn't usually create the sound, but its density and composition affect how the sound wave propagates, which frequencies travel farthest, and how clear the signal remains. The cosmic neutrino background is that medium for gravitational waves. The potential imprint is incredibly subtle, a faint modulation on an already faint signal. Yet, if we could detect it, it would open a direct window into that pivotal first second. It would confirm not only the existence of this sea of relic neutrinos, which has never been directly detected, but also tell us about their properties, like their total mass and how they behaved in the infant cosmos. The first ripples would carry a whisper about the ghostly traffic jam they had to navigate, a permanent record of the universe's first great thinning, when the neutrinos went their own way and left their mark on the fabric of space-time itself. Hidden within the mathematics of the strong nuclear force lies a puzzle so precise it demands a new particle. This is the strong CP problem, a question of symmetry so fine-tuned that physicists believe nature must have provided a solution. That solution could be the action, an incredibly light, ghostly particle that has never been detected. But if actions exist, they may have woven the fabric of the early cosmos in ways that left a distinct gravitational echo. As the universe cooled from its unimaginable birth, the action field, like others, would have undergone a phase transition. Think of it like a vast cosmic magnet cooling. As it settles, its internal direction has to choose an orientation, a north pole. But in a universe expanding at light speed, different regions cannot communicate. One patch chooses its north to point up, another chooses down, and another chooses a completely different angle. Where these differently oriented domains meet, defects form in the structure of reality itself. These defects could be one-dimensional cosmic strings, unimaginably thin filaments of concentrated energy, or two-dimensional sheets called domain walls, vast, invisible membranes slicing through space. A network of these structures, a tangled cosmic web of action strings and walls, would have filled the infant universe. This network, however, is unstable. Over time, the strings would loop, vibrate, and snap. The domain walls would wiggle, collide, and tear themselves apart. Each of these violent events is a release of pure energy, shaking the fabric of space-time and generating gravitational waves. The resulting signal would be a persistent hum across a wide range of frequencies, a chorus from the decaying action network. The unique character of this hum depends entirely on the action's properties, primarily its mass. This creates an extraordinary opportunity. By listening with future space-based observatories, we would not just be detecting primordial ripples, we would be tuning into a frequency that directly tells us the mass of the action. It is a direct probe into particle physics from the universe's first moments. Finding this specific gravitational wave background could achieve two monumental discoveries at once. First, it would solve the strong CP problem, confirming a deep symmetry in the laws of nature. Second, it would unveil the mechanism that generated the universe's first space-time ripples, revealing a cosmos once crisscrossed by a vibrating network of quantum strings and walls, whose death throes still resonate through the vacuum of space today. The universe may have begun not with a bang, but with a low hum, before the grand expansion of the Big Bang, before even the concept of classical space-time as we know it. Some theories suggest a more fundamental state existed. String gas cosmology offers one such radical vision. In this framework, the earliest moments are not described by fields or particles, but by the fundamental vibrating strings of string theory. Imagine a universe so incredibly small and hot that it is filled with a dense, chaotic gas of these fundamental strings, constantly wiggling, colliding, and interacting. This is not a smooth, empty space expanding. It is a seething, tangled web of energy where the very notions of distance and geometry are derived from the collective behavior of the strings themselves. In this primordial string gas, the dynamics are governed by thermodynamics, the same principles that describe the pressure and heat of a gas in a box. The strings have winding modes, meaning they can wrap around the compact dimensions of the early universe. As the cosmos evolves from this initial state, these winding strings exert a pressure that naturally prevents a singularity, leading to a smooth transition into the expanding Big Bang phase we recognize. But during that hot, dense, pre-Big Bang phase, the string gas is anything but quiet. The constant interactions, collisions, and vibrations within this gas generate gravitational waves directly. Because the source is this stringy, thermodynamic sea, the spectrum of waves it produces carries a unique signature. Unlike the gravitational waves from inflation, which are stretched quantum fluctuations of a field, the waves from a string gas have a different character. Their power across different frequencies would follow a distinct pattern, a kind of barcode imprinted by the thermodynamics of fundamental strings. Detecting such a signal would be monumental. It would not just tell us about the universe's expansion, it would provide direct evidence for string theory itself. We would be listening to the faint, residual vibrations from a time when the building blocks of reality were not points but dancing threads, and the cosmos was a symphony of their collective heat. This theory reframes our origin from a singular geometric event to a thermodynamic process, suggesting the first ripples are not echoes of a field stretch, but the fading reverberations of a fundamental string chorus from a time before time began. Dark energy may not be a newcomer to the cosmic stage. The force pushing galaxies apart today, a mysterious repulsive energy woven into the fabric of space, might have been the universe's first and most powerful actor. This is the provocative idea of early dark energy. We picture dark energy as a modern phenomenon, a gentle pressure that only began to dominate the cosmos in its middle age around 5 billion years ago. But what if it was there from the very first instant? What if, before inflation even began, a different form of dark energy held sway, creating a brief, explosive period of expansion that set the stage for everything to come? This early dark energy would not have been the constant, subtle force we see today. Instead, it could have been a dynamic field that rapidly decayed, a short-lived burst of repulsive gravity that violently stretched the infant universe before fading away and allowing the more familiar process of cosmic inflation to take over. That fleeting moment of dominance would have fundamentally reshaped the landscape of the cosmos. Quantum fluctuations, the seeds of all structure, would have been stretched and amplified during this early dark energy phase. But because the physics of this field would differ from the standard inflaton field, it would process those quantum jitters differently. The result would be a distinct pattern imprinted on the primordial gravitational waves. Their power spectrum, the map of how strong the waves are at different frequencies, would carry a bump, a wiggle, or a specific tilt that acts as a fingerprint of this early dark energy episode. Detecting such a signature would rewrite our cosmic origin story. It would tell us that the universe's acceleration is not a one-time event but a recurring theme. The same type of repulsive force that is shaping our cosmic future also sculpted our distant past, acting as a primer that prepared the quantum canvas before the main act of inflation even began. This idea also offers a potential solution to a subtle tension in our current data. Measurements of the universe's current expansion rate from distant supernova do not perfectly align with predictions based on the ancient cosmic microwave background. Early dark energy, by tweaking the expansion history in that first fraction of a second, could provide the necessary nudge to make these two cosmic clocks tell the same time. So the hunt for the first ripples becomes a search for a cosmic double signature, evidence that the force now quietly pulling the universe apart was once its loudest, most creative voice, shouting into the void and leaving an echo we might finally be able to hear. Light may not have always been the universe's ultimate speed limit. Deep within the fiery forge of the Big Bang, at energies so high they defy comprehension, the very rules that govern space and time might have been different. This is the radical premise of Lorentz violation in quantum gravity. For over a century, Einstein's theory of relativity has been a cornerstone of physics built on Lorentz invariance. This principle states that the laws of physics and crucially the speed of light in a vacuum are the same for all observers, no matter how fast they are moving. It is the reason why nothing can travel faster than light, a cosmic speed limit woven into the fabric of reality. But this beautiful symmetry might only be an approximation, a rule that holds in our relatively calm, low-energy universe. At the Planck scale, the realm of quantum gravity where space-time itself becomes a seething, foamy quantum mess, this symmetry could shatter. In those first moments when the universe was smaller than a single atom and energies were at the Planck scale, Lorentz invariance might have been broken. The speed of light may not have been a constant, but a variable that depended on the energy of the particle or the direction it was traveling. It is a thought that upends our most fundamental assumptions. If light's speed was not the ultimate barrier, then causality itself, the unbreakable law that cause must precede effect, could have been blurred or even reversed in those initial instants. This profound shift would have completely reshaped the genesis of the universe's first gravitational waves. In a standard Lorentz invariant cosmos, gravitational waves are produced in a specific way and always travel at the speed of light with two distinct polarization modes like plus and cross shapes. But in a regime where Lorentz symmetry is broken, the production mechanism could have been wildly different. The intense gravitational interactions at the Planck scale might have generated waves with additional polarization states, strange vibrational patterns in space-time that our current detectors are not even designed to look for. Even more strikingly, these primordial waves would not have all traveled at the same speed. Higher frequency gravitational waves might have outpaced lower frequency ones, a phenomenon called dispersion. Think of it like light passing through a prism where different colors or frequencies bend at different angles. In the early universe, space-time itself might have acted like a cosmic prism for gravity, causing the highest-pitched ripples from the Big Bang to race ahead of the deeper rumbles. Over 13.8 billion years of travel, that dispersion would have left a clear mark. The signal we receive today would be smeared out, its different frequencies arriving at slightly different times, like an orchestra where the violins reach you a moment before the cellos. Detecting such a smear in the primordial gravitational wave background would be a direct ticket back to the Planck epoch. It would be empirical proof that in the universe's first violent tremors, the rules were not the rules we know. The echo we are straining to hear might not be a clean, pure tone, but a distorted chord, a direct recording of a time when light was not yet the law, and the fabric of reality was still writing its own operating manual. The event horizon of a black hole is supposed to be an uneventful place. According to Einstein's general relativity, crossing this point of no return would be smooth, a quiet passage into a region of infinite curvature. But quantum mechanics paints a far more violent picture, one that could rewrite the story of the universe's first second. This is the firewall paradox, a thought experiment so jarring it suggests the edge of a black hole might be a searing wall of energy, a literal curtain of fire that would incinerate anything falling in. The paradox arises from a fundamental clash between two pillars of physics. On one hand, quantum mechanics demands that information cannot be destroyed. On the other, our classical understanding of black holes suggests it is. To preserve information, theorists found that the event horizon must be anything but smooth. It must be a chaotic, high-energy region where quantum fields are maximally entangled, creating a blazing discontinuity, a firewall. Now, take this terrifying idea and win the cosmic clock all the way back to the beginning. In the first fleeting moments, our entire observable universe was compressed into a volume smaller than an atom. At that scale, the cosmos itself would have been governed by quantum gravity. Its boundary, the cosmic horizon from which our universe emerged, would not have been the smooth geometry of classical theory. If the firewall logic holds, that primordial horizon would have been a maelstrom of quantum fury. It would have been a seething, energetic membrane, a roiling surface of creation where the laws of physics as we know them broke down completely. This was not a gentle unfolding. It was a violent separation of the universe from whatever quantum state preceded it. The turbulence at that first horizon would have been unimaginable. Quantum fields, stretched and scrambled by the rapid expansion, would have been in a state of extreme excitation. And just as the chaotic plasma of the early universe generated gravitational waves, this primordial firewall would have done so on a scale we can scarcely comprehend. The result would have been a fierce, high-frequency burst of gravitational radiation, a shriek of space-time emitted as the universe tore itself free from its quantum gravitational origins. This signal would be distinct from the low hum of stretched quantum fluctuations from inflation. It would be more like a sharp, initial crack, a transient burst of ripples at frequencies potentially much higher than anything our current detectors can hear. Its signature would be a unique fingerprint of that first fiery boundary. Detecting even an echo of such a signal would be revolutionary. It would provide empirical evidence for one of the most contentious ideas in theoretical physics, suggesting that the firewall paradox is not just a mathematical curiosity, but a real feature of horizons, including the one that birthed our cosmos. It would mean our universe did not emerge from a calm, geometric origin, but from a quantum inferno, its first act a violent declaration of independence from the unknown, an echo of fire frozen into the very fabric of space. The vacuum of space is not empty, it is alive with a faint, seething energy. This vacuum energy, also known as the cosmological constant, is the simplest explanation for dark energy, the force accelerating the universe's expansion. But its measured value presents the most baffling fine-tuning problem in all of physics. Theoretically, we can estimate the vacuum energy's strength by summing all the quantum fluctuations of every field in existence. The calculation yields a number so astronomically large, it would have torn the universe apart in a fraction of a second. Yet the value we actually observe is almost exactly zero, smaller than the prediction by a factor of 1 followed by 120 zeros. It is like calculating the explosive force of every nuclear weapon on Earth, only to measure the gentle pressure of a single grain of sand. This discrepancy is the cosmological constant problem, and it screams that something is missing from our story. Many theorists believe the resolution must lie in the universe's first moments. Perhaps a mechanism existed that dynamically relaxed the vacuum energy, cancelling out the enormous quantum contribution until only this tiny, leftover sliver remained. One compelling idea is that the early universe sampled many different vacuum states, a vast landscape of possibilities with different values for the constants of nature. In this landscape, only regions where the cosmological constant was incredibly small, like ours, could become stable and expansive enough to form galaxies, stars, and ultimately, observers like us. This is the anthropic argument. We find ourselves in a universe with a tiny cosmological constant because it is the only kind of universe we could exist in. But the process of settling into this specific, finely tuned vacuum would not have been silent. As the infant cosmos navigated this landscape of possibilities, it might have undergone phase transitions, tunneling between different vacuum states. Each transition would have been a violent event, releasing energy as the universe settled into a lower energy configuration. These repeated tunnelings and relaxations would have shaken the fabric of space-time, generating a cacophony of gravitational waves. The resulting spectrum of primordial ripples would carry a specific signature of this dynamical relaxation process. Alternatively, there could be a field, a kind of cosmic thermostat, that actively adjusted the vacuum energy in the early universe, rolling down a potential until it reached the precise, nearly zero value we see today. The oscillations of this field as it settled into its minimum would also have produced gravitational waves. The key is that the solution to the greatest fine-tuning puzzle we know might be written in the language of the first gravitational waves. If we detect a primordial background with a specific pattern, perhaps one with features at multiple frequencies indicating a series of steps or a particular oscillatory decay, it could be the direct echo of the universe cancelling its own vacuum energy down to that inexplicably tiny number. It would mean the first ripples are not just a byproduct of expansion, but the sound of the cosmos solving its most profound existential crisis, tuning itself from a state of impossible violence into the stable, life-friendly reality we call home. Space-time itself might have been a blurry, undefined thing. This theory, called non-commutative geometry, proposes that in the universe's first moments, the very coordinates of space and time did not have a definite order. In our everyday world, it doesn't matter if you measure a room's length and then its width, or its width and then its length, the result is the same. The measurements commute, but in the quantum realm this is not true. For a particle, measuring its position and then its momentum gives a different result than measuring its momentum and then its position. There is a fundamental uncertainty built into reality. Non-commutative geometry applies this quantum principle to the fabric of the cosmos itself. It suggests that at the Planck scale, the labels we use for here and now become fuzzy. The concepts of before and after lose their sharp meaning. Space-time is not a smooth, continuous stage but a seething quantum foam, a probabilistic froth where geometry itself is defined by relationships that do not commute. In such a chaotic, pre-geometric state, our familiar idea of a gravitational wave, a smooth, propagating ripple in a classical space-time fabric, simply does not exist. There is no smooth fabric to ripple, so how could the primordial gravitational waves we search for ever emerge? The answer lies in a process akin to condensation. As the universe expanded and cooled from this quantum foam, a phase transition occurred. The fuzzy, non-commutative relations between coordinates began to settle, to crystallize into the classical, smooth geometry we experience today. It is like watching a turbulent, choppy sea gradually calm into a placid lake with clear, predictable waves. The gravitational wave signal we hope to detect would not be a direct product of that initial foam. Instead, it would be an emergent phenomenon, a collective pattern that only becomes defined as the universe transitions from quantum chaos to classical order. The properties of that final signal, its spectrum, its polarization, would carry the indelible scars of its birth. They would encode the specific rules of that underlying non-commutative algebra, the mathematical recipe that dictated how space-time solidified. Detecting these ripples could therefore offer a direct test of this profound idea. A specific, non-standard pattern in the gravitational wave background might be the ghostly imprint of a time when here and there were not fixed points but probabilities, and the universe's first vibrations were the sound of reality defining itself. The cosmos might not be made of stuff but of answers. This is the radical vision of physicist John Wheeler, who proposed the idea of it from bit. In this view, every particle, every force field, every event in the universe is ultimately manifested from binary yes or no questions, from bits of information. Matter and energy are not the foundation. They are the physical expression of an underlying immaterial reality built on information. This idea finds a powerful modern echo in the quest to unify gravity with quantum mechanics. If space and time are not fundamental, what are they? A growing body of thought suggests they are emergent phenomena, like the wetness of water or the temperature of a gas. They arise from something deeper, and that something appears to be quantum entanglement and information processing. Imagine the universe as a vast cosmic computer. Its most basic operations are not calculations in space, but calculations that create space. The intricate web of quantum entanglement between the fundamental constituents of reality weaves the very geometry we experience. Where entanglement is strong, space is connected. Where there is no entanglement, there is separation, a tear in the fabric. In this framework, gravity is not a fundamental force like electromagnetism. It is a thermodynamic force, an emergent effect of the system's tendency toward maximum entropy, much like the pressure in a gas emerges from countless molecular collisions. Space-time itself is a kind of hologram projected from a network of entangled quantum bits living on a lower dimensional boundary. Now, apply this to the very beginning. In that first quantum haze, before any classical geometry existed, the nascent universe would have been a seething network of potential entanglement. As it cooled and evolved, this network dynamically reconfigured, establishing new quantum connections and severing others. This process of building the cosmic entanglement web would not have been perfectly smooth. There would have been fluctuations, moments where the quantum information processing hit snags or experienced surges, and these fluctuations in the entanglement structure would have directly translated into fluctuations in the emergent geometry. They would have created ripples in the very fabric of space-time as it was being knitted together. Therefore, the primordial gravitational waves we seek might not be vibrations in a pre-existing stage. They could be the fossilized tremors from the universe's first massive act of information processing, the literal sound of reality computing itself into existence. Detecting them would be like finding the processor hum of the cosmos, a direct signal from the moment it emerged from bit. It would suggest that the deepest truth of our universe is not written in particles or fields, but in the timeless language of information, and that the first thing to ripple was not space but a quantum connection. The universe may have no beginning and no end, only an endless cycle of rebirth. Roger Penrose's conformal cyclic cosmology offers this breathtaking vision where our cosmos is just one chapter in an infinite story. In this model, time is not a line with a starting point, but a series of vast epochs called eons, each one a complete universe from its own Big Bang to its ultimate fade into darkness. Our current universe, from the fiery start 13.8 billion years ago to its cold, empty future trillions of years from now, is simply one eon in this endless chain. The radical link between them is a process called conformal rescaling. As an eon dies, all massive particles decay or are swallowed by black holes that eventually evaporate via Hawking radiation. What remains is an ocean of massless particles like photons and gravitons, flying through an exponentially expanding, nearly empty space. In this state, the universe loses all sense of scale. There is no ruler, no clock, nothing to define a meter or a second. This timeless, scale-free infinity becomes mathematically identical to the hot, dense, but also scale-free singularity of a Big Bang. Penrose proposes these two states, the remote future of one eon and the hot beginning of the next, are physically the same surface. They are stitched together along a conformal boundary, a moment where time and scale dissolve, allowing one universe to feed directly into another. Now consider the gravitational implications. In the late stages of our eon, supermassive black holes will have merged in galactic cores, sending powerful gravitational waves rippling through the cosmos. In a universe with no end, these waves would travel forever. According to Penrose's mathematics, they would not be erased at the conformal boundary. Instead, they could propagate right through it, crossing from the dying eon into the newborn one. These are not the quantum jitters of inflation, but the death throes of giants from a previous reality. As they enter the new eon, these ancient waves would imprint themselves on the earliest moments, potentially creating large-scale, circular patterns of hot and cold spots in the cosmic microwave background, anomalies on a scale far larger than inflation would typically produce. Penrose and his colleagues have searched for and believe they have found hints of these concentric rings in the CMB data, calling them Hawking points, possible signatures of supermassive black hole evaporations from a prior eon. If this is true, then the first ripples we detect might not be from our universe's birth at all. They could be cosmic ghosts, echoes from a universe that existed before time as we know it began. A fossilized tremor from an earlier reality that has bled through into our own, written on the oldest light we can see. The laws of physics sometimes allow for a state of impossible energy. In the dense, high-energy environment of the universe's first moments, certain fundamental fields might have found themselves in such a precarious position, balanced on a knife's edge where their effective mass squared became a negative number. This is the realm of tachyonic instabilities, a speculative but mathematically plausible scenario that could have violently shaken the infant cosmos. In our everyday world, a negative mass squared is meaningless. It implies a particle would have imaginary mass, a concept that leads to particles that always travel faster than light, known as tachyons. While we have never observed such particles, and they raise profound questions about causality, their mathematical possibility allows us to explore what might happen if a field temporarily entered this strange state. Picture a ball resting at the very peak of a smooth, rounded hill. This is an unstable equilibrium. The slightest nudge, the tiniest quantum fluctuation, will send it rolling uncontrollably down the slope. A field undergoing a tachyonic instability is like that ball, but the hill is inverted. Instead of resting in a stable valley, it is perched at the peak of a potential that curves downward. The moment it receives that quantum nudge, it does not roll, it plummets. The field experiences a runaway process, a catastrophic transition where its value surges from one state to another with explosive speed. This is not a gentle phase change. It is a sudden, violent lurch in the underlying fabric of reality. As the field tumbles down this inverted hill, it releases an enormous amount of energy in a very short time. That energy does not just heat the universe, it violently agitates the geometry of space-time itself. The non-linear, chaotic motion of the field acts like a cosmic drumstick beating furiously on the membrane of space, generating a storm of gravitational waves. Crucially, the character of this storm would be unique, because the instability happens rapidly and involves specific energy scales. It would produce gravitational waves with a very distinct frequency profile. Instead of the broad spectrum predicted by inflation, a tachyonic instability would create a sharp peak, a dominant note in the gravitational wave chorus. It would be like hearing a single, powerful chord ring out from the cacophony of the Big Bang, a clear signal that something snapped in the early universe. Detecting such a peaked signal would be a direct probe of physics at energies we can never hope to recreate in a particle collider. It would tell us not only that a particular field underwent this bizarre transition, but also precisely when it happened and how much energy was involved. The echo would be a forensic report from the scene of a cosmic instability, evidence that the universe's smooth expansion was punctuated by a moment of violent tachyonic turbulence, a fleeting instant where the rules seemed to invert and reality itself took a catastrophic leap into a new state. Supersymmetry whispers that every known particle has a hidden, heavier twin. This elegant idea, proposed to solve deep puzzles in particle physics, finds its ultimate expression in supergravity, a theory that marries supersymmetry with Einstein's general relativity. If supersymmetry is woven into the fabric of reality, then for every force carrying boson, there must be a fermionic superpartner. The photon has the photino. The gluon has the gluino, and for the graviton, the hypothetical quantum particle of gravity, there must be the gravitino. This particle is more than just a name on a chart. It is the linchpin of supergravity, a fermion with a spin of 3 halves that carries the force of gravity in a supersymmetric world. In the searing heat of the universe's first moments, conditions would have been perfect for producing gravitinos in staggering abundance. They would have been as common as photons in that primordial soup, a dense fog of these exotic particles. But the gravitino's story is one of dramatic transformation and potential catastrophe. As the universe expanded and cooled, most of these gravitinos would have decayed into lighter particles. The precise details of that decay are crucial. If the gravitino were unstable and decayed rapidly, it could have injected a tremendous burst of energy into the cosmos. That sudden release would have violently shaken the fabric of space-time, much like throwing a boulder into a still pond. The resulting shockwaves would have been a potent source of primordial gravitational waves, their frequency and amplitude directly tied to the gravitino's mass and lifetime. The echo we seek could literally be the sound of the gravitino's death. Alternatively, if the gravitino were stable or very long-lived, it presents a different scenario. These relic particles would have drifted through the early universe as a form of dark matter, their sheer gravitational presence influencing how structures formed. Their collective motions, their flows and interactions in the dense early plasma, could have generated gravitational waves through their gravitational pull alone, a low hum from a sea of invisible particles. But there is a profound link here to our largest experiments on Earth. The properties of the gravitino, its mass, its coupling strength, are dictated by the same supersymmetry that physicists hunt for at the Large Hadron Collider. Finding a superpartner like the photino or the gluino at CERN would not just confirm supersymmetry, it would give us the rulebook for the gravitino. We could then calculate with precision how many were made in the Big Bang, how they decayed, and exactly what kind of gravitational wave signal they should have produced. The hunt for the first ripples thus becomes a cosmic cross-check. A detection from space that matches the prediction from collider data would be a triumph of unification, proving that the laws governing the smallest particles also orchestrated the largest structures in the sky. It would mean the faintest tremor from the dawn of time carries the fingerprint of a particle we might soon create in a tunnel beneath the Swiss-French border, connecting the ultimate frontiers of the very large and the very small. Gravity might have a hidden-handedness. In the standard picture, a gravitational wave is a symmetric ripple, stretching space in one direction while squeezing it in the perpendicular direction, then reversing the pattern. This oscillation can be thought of as 2 fundamental states, like the left and right circular polarizations of light. In Einstein's theory, these 2 states are perfect mirror images, propagating through the cosmos at exactly the same speed. But what if they are not? A profound modification to gravity, known as Chern-Simons gravity, introduces a term that breaks this mirror symmetry, a phenomenon called parity violation. In this framework, the fabric of space-time itself would treat left-handed and right-handed gravitational waves differently. One polarization might travel slightly faster or be amplified relative to the other as they journey through the universe. This effect is gravitational wave birefringence, analogous to how certain crystals split a beam of light into 2 rays that travel at different speeds. Now, wind this idea back to the universe's first moments. If the Chern-Simons term was active during inflation or another primordial epoch, it would have imprinted a distinct chirality, a handedness, onto the storm of gravitational waves being generated. The resulting background would not be an equal mix of left and right circular ripples. It would be skewed. One-handedness would dominate, creating a net circular polarization in the primordial gravitational wave signal. This would be a cosmic signature of breathtaking specificity. Detecting it would be far more than just confirming the existence of the first ripples. It would tell us that the force of gravity itself operated under different asymmetric rules at the highest energies. It would be direct evidence that Einstein's magnificent theory, while overwhelmingly successful, is an approximation of a deeper, more complex truth that emerges in extreme conditions. This chiral fingerprint would also serve as a powerful discriminator between theories of the early universe. Many models, from certain string theory constructions to theories involving dynamical fields that couple to gravity, naturally predict such parity-violating terms. Finding a handed signal would immediately elevate a handful of theories while ruling out a vast swath of others that predict a symmetric outcome. The hunt, therefore, becomes a search for a cosmic spin, a preference in the twist of space-time that has been frozen into the universe's gravitational memory since the first fraction of a second. Gravity itself may have once been a boiling liquid. Before the universe was even a trillionth of a second old, the conditions were so extreme that the fundamental building blocks of reality behaved in ways we can barely conceive. In this unimaginable forge, all particles, including the hypothetical carriers of gravity known as gravitons, were in a state of perfect thermal equilibrium. They were constantly colliding, interacting, and exchanging energy with everything else in the seething plasma, from photons to quarks. Gravity, in this epoch, was not a distinct geometric force shaping a smooth stage. It was just another ingredient in a quantum soup, its quanta jostling and bouncing like all the others. This is the realm of the thermal graviton gas, a fleeting moment when gravity was thermalized. For this to happen, the universe had to be hotter and denser than at any other point in its history. The energy was so high that the typical distance between particle collisions was shorter than the characteristic wavelength of a graviton. In simpler terms, gravitons could not travel far before smashing into something else. They were trapped, constantly interacting, unable to propagate freely as waves across the cosmos. They were prisoners of the heat, but this state could not last. As the universe expanded at a ferocious rate, it cooled. The density dropped. Suddenly, the distance between particles grew larger than the graviton's wavelength. The collision stopped. In an instant, gravitons fell out of thermal equilibrium. They decoupled from the rest of the cosmic plasma. This was a profound phase transition, not of matter, but of a fundamental interaction. Gravity went from being a thermalized, interacting fluid to a free, propagating force. The moment of decoupling would have been violent. Think of it like the sudden freezing of a supersaturated liquid. The system is unstable, eager to change state. As the gravitons broke free, the energy and momentum of that transition had to go somewhere. It shook the very geometry they were beginning to define. This violent relaxation, this settling into a new classical reality, would have generated a storm of gravitational waves, and because the source was a thermal process, the resulting waves would carry a specific telltale signature, a thermal spectrum. Unlike the stretched quantum fluctuations of inflation, which have a very particular tilt, a thermal spectrum has a different shape. It is the fingerprint of heat, of random collisions, rather than of quantum uncertainty stretched across the sky. Detecting such a spectrum in the primordial gravitational wave background would be a direct window into that pre-Planckian soup. It would tell us that there was a time when gravity was not yet the serene geometric force we know, but a seething, thermalized component of a unified quantum chaos. The echo would be the sound of gravity cooling down, crystallizing out of the primordial inferno to become the architect of the cosmos we recognize. The singularity is a warning sign. At the heart of a black hole, and at the beginning of our universe, our equations break down, predicting a point of infinite density where the laws of physics cease to apply. But what if infinities are not real? Loop quantum gravity, a rival to string theory, offers a radical escape clause. It suggests that space-time is not a smooth continuum, but woven from a fabric of tiny, indivisible loops, a quantum tapestry with a finite, smallest possible stitch. This discrete structure acts like a cosmic safety net, preventing the infinite collapse of a singularity. In this view, the Big Bang was not a beginning from nothing, but a big bounce. Our universe is the rebounding expansion from the collapse of a previous cosmic epoch. The crushing density reached a maximum governed by the Planck scale, and then quantum geometry provided a repulsive force, a spring that pushed back, initiating our expansion. This idea extends beautifully to black holes. Instead of a point of no return ending in oblivion, a black hole's core might not be a singularity. As matter is compressed to the Planck density, the loops of space-time reach their maximum tension. The collapse stops and a rebound begins. The result is a Planck star, a hypothetical object of unimaginable density, trapped inside the event horizon of the black hole. From our perspective outside the horizon, this rebound would take an agonizingly long time due to intense gravitational time dilation. But in its own frame of reference, the star forms and begins to expand in a flash. Now picture the universe in its first searing moments. If the Big Bang itself was a bounce from a prior cosmos, then the conditions were ripe for the spontaneous quantum creation of microscopic black holes, each a universe in miniature. These primordial black holes would have formed, lived, and then rebounded as tiny Planck stars almost instantly. The early universe would have been a fireworks display of quantum gravitational rebounds, a frothing sea of micro-bounces within the grand bounce of the cosmos itself. Each rebound, each transition from collapse to expansion, is a violent event. The sudden reversal, the release of quantum gravitational pressure, would send powerful ripples cascading through the fabric of space-time. The collective chorus of countless such events, a statistical roar from a universe being born from a billion tiny rebirths, could generate a dominant stochastic background of gravitational waves. The character of these waves would be unique because the source is a quantum gravitational process with a fundamental scale. The spectrum of the waves might show a cutoff or a specific feature at high frequencies, a direct imprint of the discrete nature of space-time. Detecting this would be a twofold revolution. First, it would tell us that black holes are not eternal tombs, but transient structures with a fiery quantum core. Second, it would confirm that our entire universe is cyclic, one bounce in an endless sequence, and that the first ripples we hear are not the sound of creation, but the sound of recreation, the echo of a cosmos that has done this all before. The deepest mystery is not how the universe began, but why it has a past, present, and future. The emergent time hypothesis confronts this head-on, suggesting that time itself is not a fundamental ingredient of reality. It is something that crystallized, an illusion that emerged from a more basic, timeless quantum state. In this view, the universe did not begin in time. It began, and time began with it. Before that moment, the question of when had no meaning. There was no flow, no arrow, no clock. The cosmos existed in a state of pure potential, a quantum superposition of every possible configuration, frozen in an eternal now. Then something broke the symmetry. A process called decoherence took hold. The infinite possibilities of that timeless state collapsed into a single, concrete history. The universe chose a path, and in doing so, it defined a direction. That first choice, that initial branching from potential into actuality, created the very first moment. It was the birth of cause and effect, the instant the cosmic film reel began to roll. This transition would not have been silent. Moving from a timeless quantum fog into a universe with a definitive arrow of time is a cataclysmic shift in the structure of reality. The energy released in that crystallization would have been immense, violently shaking the nascent geometry of space as it snapped into a form that could support a flowing timeline. The result would have been a burst of gravitational waves, a literal shockwave from the birth of time. This idea reframes the first space-time ripple in a breathtaking way. The gravitational wave background we search for might not just be an echo of expansion or collision. It could be the fossilized sound of time switching on. The faint hum would be the first tick of the cosmic clock, a permanent record of the moment the universe transitioned from a state of being to a story of becoming. Detecting it would be like finding the start button for history itself. It would suggest that our relentless march from past to future is not a law written in stone, but a phase the universe is going through, an emergent property that began with a tremor we might still be able to hear. Our cosmic home might be resting on a foundation of sand. This is the vacuum decay catastrophe, a theory rooted in the unsettling possibility that our universe is not in its most stable state. The vacuum of space, which we perceive as empty and unchanging, could be what physicists call metastable. It is a local valley in a vast cosmic landscape, seemingly calm and permanent, but with a deeper, lower energy valley somewhere beyond the hill. Our entire reality, from galaxies to gravity, is built upon this particular energetic configuration. If something provided a sufficient nudge, a quantum tunnel could form, and our vacuum could decay, collapsing into that lower energy state. The transition would propagate at the speed of light, rewriting the laws of physics in its wake and erasing everything we know in an instant. It is the ultimate existential threat, not from a star or a collision, but from the ground of being itself. Now, rewind this terrifying idea to the universe's first moments. In that primordial forge, conditions were unimaginably hot and dense. It is entirely plausible that the infant cosmos began not in our current, relatively low energy vacuum, but in a higher energy false vacuum, a more precarious perch on the cosmic landscape. As the universe expanded and cooled, it underwent a phase transition, decaying or rolling down into the stable or metastable state we inhabit today. That transition would not have been a quiet settling. The decay of a false vacuum is a violent, first-order phase transition of the most extreme kind. Think of it like a supercooled liquid suddenly and explosively freezing. Bubbles of the new, lower energy vacuum would have spontaneously formed in the seething high-energy sea. These bubbles would have expanded at nearly the speed of light, colliding and merging. The energy released at the bubble walls during these collisions is staggering, far beyond anything in a supernova. That energy doesn't just heat the cosmos, it violently shakes the very geometry of space-time. The colliding bubble walls would act like immense relativistic drums, pounding out a fierce storm of gravitational waves. This would not be the low hum of stretched quantum fluctuations. It would be a sharp, powerful burst, a distinct crack in the fabric of the newborn universe. The gravitational wave signal from such an event would carry a direct message about the stability of the primordial vacuum. Its frequency spectrum would act as a cosmic thermometer, telling us the energy difference between the false vacuum and the true one. The amplitude of the waves would reveal the tension of the bubble walls, the sheer force of the transition. If we could detect this specific burst within the primordial gravitational wave background, it would answer one of the most profound questions we can ask. Is our universe sitting in its final, eternal resting state, or are we, and everything we see, merely temporary occupants of a cosmic ledge, awaiting a quantum trigger that could erase us from existence? The first ripples could be the sound of our universe narrowly avoiding an early demise, settling into a precarious stability that has, so far, lasted for 13.8 billion years. Strings have a breaking point. In the fiery crucible of the universe's first moments, as temperatures soared to unimaginable heights, the fundamental strings of string theory would have behaved in a way that defies all our classical intuition. This is the Hagedorn phase, named after physicist Rolf Hagedorn, a state of matter so exotic it represents a thermodynamic ceiling for a universe built from strings. Picture a pot of water on a stove. As you add heat, the water's temperature rises until it reaches 100 degrees Celsius. At that point, adding more energy doesn't make the water hotter. It instead goes into breaking the bonds between water molecules, transforming the liquid into steam. The Hagedorn temperature is like that boiling point for the cosmos itself. When the universe was hotter than this critical threshold, adding energy did not primarily increase the frenetic motion of particles. Instead, the energy went into creating more fundamental strings. The universe became a dense, tangled spaghetti of strings, a chaotic soup where the distinction between matter and energy blurred into a writhing network of one-dimensional threads. It was a state of maximum entropy, a cosmic tangle where the very concept of temperature as we know it began to lose its meaning. As the cosmos expanded, it inevitably cooled. Crossing back below the Hagedorn temperature was not a gentle process. It was a dramatic first-order phase transition, akin to steam condensing violently back into water droplets. The universe had to untangle itself from this stringy soup and reorganize into a state where particles and the familiar forces could emerge. This transition would have released an enormous amount of latent energy, the energy that was tied up in the complex string network. That sudden release would have been catastrophic for the geometry of space-time. Think of it like cutting a vast, tense web of rubber bands all at once. The snap would send violent vibrations through the entire structure. In the early universe, that snap was a gravitational shock wave. The transition out of the Hagedorn phase would have generated a tremendous burst of gravitational waves, a loud, distinct signal ringing out as the cosmos crystallized from a stringy fog into a more familiar particle-based reality. The beauty of this idea is its specificity. Because the Hagedorn temperature is a fundamental number in string theory, tied to the string scale itself, the gravitational waves produced would carry its direct imprint. Their characteristic frequency would tell us the energy at which this phase transition occurred, effectively measuring the tension of the fundamental strings. Detecting such a signal would be a direct validation of string theory's core premise. It would provide concrete evidence that the building blocks of reality are not point-like particles, but vibrating strings, and that our universe endured a fleeting, turbulent adolescence as a seething string gas before settling into the cosmos we recognize today. The echo would be the sound of the universe combing out its tangled hair, a sharp snap from the moment strings decided to become stuff. The very laws of physics might be a product of our own gaze. This is the unsettling heart of the anthropic principle, the idea that the universe we observe must be compatible with the existence of observers like us. It is not a theory of creation but a filter of selection, and it applies with eerie precision to the universe's first space-time ripples. Consider the amplitude of those primordial gravitational waves, their sheer loudness. That number is not arbitrary. It is a dial on the cosmic control panel that was set with astonishing care. If the dial had been turned even slightly higher, if those initial ripples had been significantly stronger, the consequences would have been catastrophic. In the fragile early universe, gravity is the sculptor of everything. Stronger gravitational waves mean more violent turbulence in the primordial plasma. This extra churning would have added a powerful, chaotic ingredient to the mix, overwhelming the delicate density fluctuations that were slowly pulling matter together. The formation of the first stars and galaxies would have been severely disrupted, like trying to build a sandcastle in a hurricane. The cosmos might have remained a formless, swirling fog, never giving rise to the stable structures that forge heavy elements and ultimately life. On the other hand, what if the dial was turned too low? What if the first ripples were whisper quiet, almost non-existent? While this seems less destructive, it could be equally prohibitive. Those gravitational waves and the density fluctuations they are tied to are the seeds for all cosmic structure. If they are too faint, the initial clumpiness of the universe might have been insufficient. Gravity would have had almost nothing to work with. matter might have remained too smoothly distributed, failing to collapse into the dense knots that become galaxies and stars. The universe could have evolved into a vast, dark, and ever-thinning sea of isolated atoms, a cosmic desert with no islands of complexity. Our existence then hinges on a razor's edge. The amplitude of the primordial gravitational wave background had to be within a very specific, narrow window strong enough to see the cosmos, but gentle enough not to tear it apart. This precise tuning is exactly what we appear to see in our universe. So when we build ever more sensitive experiments to detect these ripples, we are not just probing the early universe. We are testing a profound philosophical idea. Our detection, or even our failure to detect a signal above a certain threshold, might tell a story far bigger than our own cosmos. It could be evidence for the multiverse, in an infinite ensemble of universes, each with randomly dialed physical constants. The parameter controlling the strength of the first ripples would take on every possible value. In the overwhelming majority of those universes, the dial is set wrong, too high or too low. Those are dead, sterile worlds, empty of observers. Only in the rare, finely tuned slices where the amplitude falls in the habitable window can galaxies, stars, planets, and life arise. We, by necessity, find ourselves in one of those rare, life-friendly bubbles. Therefore, the quiet hum we search for, or the silence we might find, is not a random accident. It is a signature of selection. It is the echo from a universe that was, against staggering odds, just right for us to be here to listen for it. That precise tuning points to an even deeper story of cosmic self-assembly. The universe did not start with four distinct forces. In its first searing moments, all of reality was governed by a single, perfect symmetry, a grand unified force that encompassed everything. As the cosmos expanded and cooled, this pristine symmetry began to crack, not once, but in a series of cascading fractures. Think of it like a pane of glass cooling from a molten state. As it solidifies, internal stresses build. The glass wants to settle into a stable, crystalline structure, but it cannot decide on a uniform pattern all at once. So it cracks, and then those cracks branch into smaller cracks, creating a complex web of fractures. Our universe underwent a similar process, a symmetry-breaking cascade. The first and most dramatic break happened when gravity peeled away from the grand unified force. Then, as temperatures plummeted further, the strong nuclear force separated from the electroweak force. Finally, the electroweak force itself split, giving us the distinct electromagnetic and weak forces we recognize today. Each of these breaks was a cosmic phase transition of unimaginable scale, a moment when the very rules of physics changed in different regions of space. And like water freezing into ice, these transitions were not perfectly smooth. When a symmetry breaks, different parts of the universe can make different choices about how to settle. One region might choose one orientation for its quantum fields, while a neighboring region chooses another. Where these differently oriented domains meet, defects form in the fabric of reality itself. These are not mere imperfections. They are topological defects, stable structures dictated by the mathematics of the broken symmetry. Depending on the type of symmetry that broke, these defects could be point-like magnetic monopoles, one-dimensional cosmic strings, or two-dimensional domain walls, vast, invisible membranes slicing through space. Each defect is a fossil, a relic of a specific moment in the cooling cosmos, and their formation would have been anything but quiet. The energy locked into these defects is staggering. As cosmic strings vibrate, snap, and loop, or as domain walls collide and annihilate, they release tremendous bursts of energy directly into the fabric of space-time. Each event is a hammer blow on the cosmic drum, generating powerful gravitational waves. The first ripples we search for, then, might not be a single, pure tone from one event. They could be a layered symphony, a palimpsest of gravitational echoes. the lowest frequencies might carry the deep rumble from the earliest, most energetic break when gravity divorced itself from the unified whole. Mid-range frequencies could hold the sharper notes from the strong force breaking free, and the highest frequencies might still resonate with the last, finer cracks of the electroweak split. This cascade paints a picture of a cosmos that found its identity through a sequence of violent crystallizations. Detecting this gravitational wave background and deciphering its spectrum would be like listening to a cosmic recording of the universe growing up. We would hear the specific moments when the forces of nature, once united, went their separate ways, each break leaving a permanent vibrational signature in the geometry of everything. It would tell us not just that the universe cooled, but precisely how it chose to structure itself, layer by layer, from perfect unity to the rich, complex, and broken reality we call home. This crystallization would have been a sonic boom for reality itself. We are familiar with the concept from fighter jets. When a plane accelerates through the speed of sound, it compresses the air ahead of it into a powerful shockwave, a thunderclap that ripples through the atmosphere. Now translate that idea to the birth of the cosmos. In its very first instant, the universe was not a smooth, expanding stage. It was a seething quantum foam, a probabilistic froth where notions of here and there, before and after, had no definite meaning. Space and time were not yet the continuous, reliable dimensions we navigate. They were a chaotic, fluctuating quantum potential. Then, as the universe expanded and cooled, a profound threshold was crossed. The energy density dropped below a critical point. The chaotic quantum foam underwent a phase transition, freezing into the classical, smooth geometry of space-time we know. This was the moment the universe broke its own quantum gravity barrier, and just like a jet breaking the sound barrier, that sudden transition from one state to another would have released a shockwave. But this shockwave was not made of compressed air. It was a violent ripple in the very geometry that had just been born, a gravitational wave boom. This would not be the stretched, low hum of inflationary quantum fluctuations. This would be a sharp, transient burst, a crack in the cosmic dawn. Its frequency and energy would be a direct probe of that transition moment, telling us the exact energy scale at which quantum gravity gave way to Einstein's classical universe. Detecting such a signal, perhaps as a distinct spike in the gravitational wave background at very high frequencies, would be like finding the birth certificate of space-time itself, signed with a thunderclap from the moment reality decided to become real. The final theory asks if our universe is even real. The simulation hypothesis suggests that everything we experience, from the stars above to the very fabric of space-time, is a product of an unfathomably advanced computational process. We are not beings in a base reality, but sophisticated informational patterns running on a substrate we can never perceive. It is a fringe idea, more philosophy than testable physics, yet it forces a startling question about the echoes we chase. If our cosmos is a simulation, then the primordial gravitational wave background is not a relic of a physical Big Bang. It is part of the initial conditions, a preset parameter in the cosmic code, or perhaps even an artifact, a rounding error from the first tick of the simulation's clock. Think of a video game world being generated. The developers must define the rules: gravity, light speed, the strength of forces. They also set the starting state, the seed number from which all complexity grows. In our universe, that seed includes the pattern of the first density fluctuations and their accompanying space-time ripples. Their specific amplitude and spectrum would be a choice made by the programmers, a line of code defining the initial noise from which galaxies would later form. But simulations are not perfect. Even the most powerful computer has finite resolution. When modeling something as chaotic as the birth of a universe, approximations must be made. At the Planck scale, where quantum foam should reign, the simulation might hit a limit. It cannot compute infinite detail, so it rounds off. That rounding could introduce very subtle, non-random patterns into the fabric of space-time. These would not follow the smooth predictions of inflation or phase transitions. Instead, they might manifest as anomalies in the gravitational wave background, strange, repeating correlations across different frequencies, or an unexpected cutoff at the highest energies, like pixels becoming visible when you zoom in too far on a digital image. Some have speculated that such a cosmic glitch could appear as a preferred direction in the ripples, a subtle axis that breaks the universe's perfect isotropy, hinting at the underlying grid of the simulation's processor. Or perhaps the signature would be a strange discreteness in the signal, as if the waves were not continuous but quantized in a way that reveals the finite step size of the simulation's time evolution. Searching for these anomalies is not about confirming the simulation hypothesis outright, that may forever lie beyond science. It is about stress testing our reality to its absolute limits. If we ever detect a pattern in the first ripples that defies all natural explanation, a signature that looks more like a constraint or a bug than a law of physics, we would be faced with an unnerving possibility. The most fundamental signal from the dawn of time would not be a message from the birth of a universe, but a trace of its construction, a whisper from outside the system, hinting that our quest for ultimate origins has led us to the edge of the code. From the elegant stretch of cosmic inflation to the violent crash of colliding branes, from the quiet hum of action strings to the simulated glitch of a programmed reality, we have wandered through 30 astonishing landscapes of origin. Each theory, whether grounded in decades of research or dancing on the edge of speculation, represents a profound attempt to decode the universe's first whisper. This is the true power of the hunt for primordial gravitational waves. A confirmed detection would do far more than crown a single winning idea. It would shatter the opacity of the universe's first moments, swinging open a direct window to an era forever beyond the reach of particle colliders, the Planck epoch itself. We would gain a physical recording from the frontier where gravity became quantum, a data set against which every grand theory of everything from string theory to loop quantum gravity must be tested and measured. The faintest tremor in space-time is a key to the foundations of physics, so we turn the question to you. In this grand cosmic menu of possibilities, which origin story resonates most deeply? Does your imagination lean toward the cyclic poetry of a bouncing cosmos, the holographic mystery of an emergent reality, or the elegant fine-tuning of the anthropic principle? Share your thoughts in the comments below. Let's continue this conversation about where everything came from. And if you crave more journeys to the edge of understanding, be sure to subscribe. Our next deep dive into the universe's great mysteries is already waiting.